Hi, I'm so happy you're here. I'd love to know where you're listening from, so comment down below where you're from. Now take a deep breath, let your mind rest, and we'll drift into the first section. Deep beneath your feet, far below the soil and stone you might imagine, if you closed your eyes and thought downward, the earth is warm. Not just pleasantly warm like a sunlit rock or a heated room, but warm enough that the very nature of rock begins to change. At these depths, measured in tens and sometimes hundreds of kilometers, the pressure is immense, the weight of all the overlying rock pressing down, and the temperature climbs steadily with each kilometer of descent. In these conditions, rock that would be rigid and brittle at the surface becomes something else entirely. It softens. It flows, though not quickly, not like water rushing through a channel. Instead, it moves the way honey might move if you left it undisturbed for years, a slow plastic deformation that happens grain by grain, crystal by crystal, over timescales that dwarf human experience. This is where magma begins, not as a sudden event, but as a gradual process of transformation. Magma is molten rock, but it doesn't form everywhere beneath the Earth's crust. It requires specific conditions, a particular alignment of heat, pressure, and chemistry. Near the boundaries where tectonic plates meet, the Earth's internal machinery creates these conditions. Where plates pull apart, the pressure on the underlying rock decreases slightly, and this reduction in pressure lowers the melting point just enough for solid rock to begin melting. Where plates collide and one slides beneath the other, water carried down with the descending plate seeps into the hot rock above. And water has a remarkable effect on melting temperature. It acts as a flux, lowering the temperature at which rock will melt, allowing magma to form in places it otherwise wouldn't. And in some regions, far from plate boundaries, there are hot spots, mysterious upwellings of especially hot material from deep within the mantle, plumes of heat that rise and create pockets of melt, even in the middle of stable continental or oceanic crust. In any of these settings, magma doesn't appear all at once. It forms in small percentages first, tiny droplets of liquid rock scattered through a matrix of still solid mineral grains. As more melting occurs, these droplets find each other, coalescing, gathering, forming larger pockets. The magma is less dense than the surrounding solid rock. Molten material is almost always less dense than its solid form. And this difference in density creates a gentle, buoyant force. The magma begins to rise, not in a rush, but slowly, seeking pathways through the rock above. It moves through cracks, through zones of weakness, through spaces between mineral grains. Sometimes it travels only a few hundred meters before cooling and solidifying again. Sometimes it finds a more sustained pathway and rises farther, journeying upward through the crust over years or decades or centuries. The pace of this movement is difficult to comprehend from a human perspective. We think of rising as something quick, like a bubble in water or smoke in air. But magma, rising through tens of kilometers of rock, is measured differently. It might rise a few meters per year or a few centimeters, depending on the viscosity of the melt and the permeability of the surrounding rock. Viscosity matters enormously here. Some magmas are rich in silica, the same chemical component that makes up quartz and glass. And these silica-rich magmas are thick and sticky, resistant to flow. Others are poor in silica, but rich in iron and magnesium. And these flow more readily, more fluidly, though still far more slowly than any liquid you've ever poured. The rising magma carries heat with it. warming the rock it passes through, sometimes causing additional melting, sometimes simply transferring its thermal energy to the cooler surroundings. As the magma rises, it eventually encounters a region where it can no longer easily continue upward. Perhaps the rock above is too cold, too strong, too impermeable. Perhaps the pathway narrows or closes off. The magma slows, pools, begins to accumulate in a space that geologists call a magma chamber or magma reservoir. This is not a hollow cave filled with liquid rock, though that image sometimes appears in illustrations. Instead, it's more accurate to think of it as a zone within the crust where the percentage of melt is high enough that the rock has lost its rigidity, where solid crystals float in liquid, where the boundary between solid and liquid is blurred and complex. The chamber is not static. It grows as new magma arrives from below, shrinks as magma crystallizes and solidifies, and shifts in temperature and composition as different pulses of melt mix together or remain separate. This accumulation happens in pulses, separated by time. A batch of magma rises and arrives. Then there is quiet for years or decades, while conditions deep below prepare another batch. The chamber is not filling constantly, like water flowing into a bathtub. It receives its magma in episodes, irregular and patient. Between these arrivals, the chamber is far from dormant. The magma inside is hot but cooling, and as it cools, crystals begin to form. Minerals with high melting points crystallize first, growing slowly, their geometric shapes reflecting the orderly arrangement of atoms in their crystal lattices. These crystals are denser than the remaining liquid, and many of them sink, settling to the bottom of the chamber, a slow mineral snow falling through molten rock. This process changes the composition of the remaining magma, making it richer in the components that haven't yet crystallized, altering its chemistry in ways that will influence what happens later. Above this deep reservoir, the surface of the earth shows no sign of the activity below. There is ordinary land, soil, vegetation, streams, the daily cycle of weather. Rain falls and soaks into the ground. Plants grow and die and decompose. Animals move through their habitats, unaware of the heat and pressure building far beneath them. The mountain or hill that will eventually be recognized as a volcano may already exist, built from previous eruptions that happened long ago, or it may not yet exist at all. The volcano still entirely hidden, a potential waiting to express itself. In either case, the surface is patient. It waits without urgency. But the earth is never entirely still, and the magma chamber, even in its quiet holding pattern, exerts subtle influences on the world above. The rock surrounding the chamber is heating slowly. Thermal expansion causes this rock to take up slightly more space, and though the expansion is tiny on a grain-by-grain basis, when integrated across cubic kilometers of crust, the effect becomes measurable. The ground surface may rise by a few centimeters, or a few tens of centimeters, over months or years. This is called inflation, the gentle swelling of the land, and it's one of the first signs that something is changing below. At the same time, the heating and pressurization of the rock causes stress to accumulate. Rock is strong, but it's not perfectly elastic. As stress builds, tiny fractures form and grow, releasing that stress in small increments. Each fracture creates a tiny earthquake, a seismic tremor far too small to be felt by anyone standing on the surface, but detectable by sensitive instruments. These micro-earthquakes cluster around the magma chamber and along the pathways where magma has moved or might move. They create a pattern, a cloud of seismic activity that outlines the shape of the system below. If seismometers are in place, monitoring the region, scientists can see this pattern developing, can watch the tiny dots of earthquake locations, mapping out the hidden plumbing of the volcano. Water also responds to the heat below. Groundwater circulating through fractures in the rock comes into contact with hot rock or directly with the magma chamber's outer edges, and it heats up. Hot water is less dense than cold water, and it rises, creating convection cells that bring heat toward the surface. Springs that were once cool may warm. Their chemistry may change as the heated water dissolves different minerals from the rock it passes through. Gases dissolved in the groundwater: carbon dioxide, hydrogen sulfide, sulfur dioxide, may come out of solution as the water heats, creating bubbles, giving the water a fizzy or acrid quality. Steam may begin to vent from cracks and fissures where the ground is thin or fractured enough to provide a pathway. This steam is just water vapor, the same steam from a kettle. But its presence at the surface is a message from below. Heat is here, and it's finding its way out. These early signs are not alarming. They are gentle, gradual, easily missed if no one is paying attention. A slight rise in the land that only GPS instruments would notice. Tiny earthquakes that require seismometers to detect. A warm spring that local people might appreciate without wondering why it warmed. The earth is clearing its throat, a quiet signal that the system is waking, but waking slowly, without haste. There is no need to rush. The volcano operates on its own timeline, and that timeline is measured in years, not days. As more time passes, the magma chamber may continue to receive new pulses of magma from depth. Each new arrival adds volume, adds heat, adds pressure. The older magma in the chamber, already cooling and crystallizing, is rejuvenated by this influx of fresh, hotter material. The temperature rises again. More crystals dissolve back into the melt. The chamber becomes more liquid, more mobile. The pressure inside increases, not suddenly, but incrementally, like a slow, deep inhale that takes years to complete. This pressure is exerted on the walls of the chamber, on the rock that contains it. And that rock must respond. It flexes, it fractures, it adjusts. But even with all this activity, the surface may remain calm for a very long time. A magma chamber can exist for thousands or tens of thousands of years without producing an eruption. During these long, quiet periods, the volcano is not inactive. It is active in slow, internal ways. Magma is crystallizing, differentiating, changing composition. The chamber is cooling around its edges, forming a shell of partially solidified rock that insulates the hotter interior. Gases are exsolving from the magma as pressure decreases slightly, or as composition changes, forming bubbles that rise through the melt and accumulate at the top of the chamber. All of this is happening invisibly, deep below, while the surface goes about its ordinary existence. This is the volcano's middle life, the era of repeated cycles. Long quiet, brief release, then long quiet again. Most volcanoes spend most of their existence in the quiet phases, the dramatic moments, the eruptions that capture human attention and fill documentaries, are brief interruptions in a much longer story of stillness. It's worth dwelling on this idea, allowing it to settle into your mind as you relax into sleep. Pressure can exist without panic. A system can be active without being urgent. The Earth holds these forces patiently for as long as it needs to, and when release comes, it comes naturally, in its own time. When the conditions are finally right, when enough pressure has accumulated and the magma has enough gas and heat and mobility, a pathway may open from the chamber toward the surface. This doesn't happen all at once. It begins with small fractures, connecting, extending, forming a conduit. Magma begins to move into this conduit, driven upward by the pressure difference between the chamber and the surface, by the buoyancy of gas-rich melt, by the force of new magma arriving from below and pushing the older magma ahead of it. The movement is slow at first, exploratory, the magma testing the pathway, finding its way through. As the magma rises, the pressure around it decreases. This is simply a consequence of having less overlying rock. Less weight pressing down means less pressure. And as pressure decreases, something important happens to the gases dissolved in the magma. All magmas contain dissolved gases, primarily water vapor, but also carbon dioxide, sulfur dioxide, and others. These gases are dissolved in the molten rock, the way carbon dioxide is dissolved in a bottle of soda. As long as the pressure is high, the gases stay dissolved. But when pressure drops, the gases come out of solution. They form bubbles. This exsolution of gas is gradual at first. Small bubbles nucleate, grow, rise through the viscous liquid. But as the magma continues to rise and pressure continues to drop, more and more gas comes out of solution, and the volume of bubbles increases. The magma becomes frothy, expanding as the gas takes up more and more space. In low viscosity magmas, the ones that flow more easily, the bubbles can rise quickly and escape, and the magma degases relatively peacefully. But in high viscosity magmas, the sticky silica-rich ones, the bubbles get trapped, unable to rise quickly through the thick melt. The pressure inside these trapped bubbles builds. The magma becomes even more expanded, even more gas-rich, and the potential for a more energetic release increases. The first part of this release, when it finally reaches the surface, might be gentle. A low rumble, felt more than heard, a vibration in the ground that comes from the movement of magma and the fracturing of rock below. A deep breath of steam as the first gas-rich magma reaches the surface and the gases escape into the atmosphere. The steam rises, a white or pale grey column, cooling as it climbs, condensing into a cloud that drifts with the wind. This is water vapor mostly, the same substance that forms clouds and fog, but carried upward by the heat and pressure of the Earth's interior. If ash begins to emerge, it appears as a darker component in the plume, fine particles of pulverized rock, glass shards formed when magma fragments, tiny crystals broken free from larger masses. Ash is not burning material. It's not like the ash from a fire. It's rock, powdered to a fine dust by the explosive expansion of gas or the grinding of magma against rock as it moves through the conduit. The particles are small, some of them microscopic, and they catch the light in particular ways, darkening the plume, giving it a gray or brown or black appearance, depending on the composition of the magma and the intensity of the fragmentation. This ash rises with the gas, carried upward by convection, by the heat of the eruption creating a buoyant column of hot air and particles. The column can rise high, kilometers into the atmosphere, driven by the continuous supply of heat and gas from below. As it rises, it cools, and as it cools, its buoyancy decreases. Eventually, it reaches a height where it can rise no farther and it begins to spread sideways, forming a mushroom-shaped cloud, a shape created by simple fluid dynamics, the same physics that govern thunderstorm clouds and smoke from large fires. The ash within this cloud begins to fall, pulled down by gravity, the larger particles falling first, the smallest particles drifting on air currents, traveling farther before settling. The ash falls softly, a gray snow that blankets the landscape. It's quiet as it settles, accumulating in layers, covering plants and rocks and buildings, if any are present. Up close, each particle is a tiny shard of glass or a fragment of crystal, angular and rough-edged. But from a distance, the falling ash is gentle, almost serene, a slow descent that can last for hours or days, depending on the size of the eruption and the height of the plume. The layer it leaves behind is a record, a marker in time, a signature of this particular release of the volcano. If the magma itself reaches the surface in liquid form, it's called lava. Once it emerges into the open air, lava is simply magma that has made it all the way from depth to daylight. It flows according to its viscosity and the slope of the land. Low viscosity lavas, the basaltic ones rich in iron and magnesium, flow readily, spreading out in broad, thin sheets or channeling into narrow streams that can travel kilometers from their source. They glow orange or red with heat, especially at night when the contrast with the dark surroundings makes the incandescence visible. The glow is thermal radiation, photons emitted by the hot material, the same phenomenon that makes a heating element on a stove glow red. These flows move slowly enough that their progress can be measured in meters per hour or meters per day. They are not rushing floods. They are thick, heavy, deliberate movements of molten rock, constrained by gravity and their own viscosity. At the edges of the flow, where the lava is exposed to air, it cools quickly. The surface hardens, forming a dark crust, a skin of solid rock that insulates the still, molten interior. Beneath this crust, the lava continues to flow, sometimes breaking through the crust to form new lobes, sometimes flowing beneath it in tubes and channels that can carry heat and liquid rock much farther than an open flow could. The contrast between the glowing interior and the dark crust is a lesson in thermal dynamics. Heat moves from hot to cold, and the air is much colder than the lava, so the surface loses heat rapidly. But rock is also a poor conductor of heat, so the interior stays hot, keeps flowing, protected by its own outer shell. You can watch this process in miniature if you pour thick liquid and let it cool. The surface sets while the interior remains fluid, and the lava flow is the same principle, scaled up to thousands of tons of molten rock. High viscosity lavas, the ones rich in silica, flow differently. They are so thick, so resistant to flow, that they barely move at all. They pile up near the vent, forming steep-sided domes or short, blocky flows. Their surfaces are rough, broken into angular fragments by the stress of the viscous interior trying to move. They cool more slowly because they are thicker, and they can remain hot at the core for months or years after the eruption ends, glowing faintly at night, steaming in the rain. A stubborn pocket of heat, gradually surrendering to the cooler world around it. Throughout all of this, the tone remains calm. This is not a disaster. This is a natural pressure valve, operating as it has for billions of years, since the Earth first cooled enough to have a crust. The volcano is not raging. It is releasing. It is letting go of accumulated pressure in the way that the Earth's systems have evolved to do. There is no malice, no anger, no emotion at all. There is only physics. Heat rising, pressure equalizing, materials moving from where they are, abundant to where they are, less so, the patient working out of natural forces. And then, after the release, comes the quieting. The supply of magma slows, thins, stops. The pressure that drove the eruption has been relieved, at least partially. The conduit may remain open for a while, venting gas and steam, but the flow of lava ceases. The ash plume diminishes, shrinks, fades to occasional puffs of steam. The ground stops shaking. The volcano transitions back into quiet. The ash that has fallen settles into the landscape. Rain begins to work on it immediately, washing the finest particles into streams, cementing the larger particles together into a soft, cohesive layer. The ash is rich in minerals, and as it weathers, it releases nutrients, potassium, phosphorus, calcium, trace elements that plants need. In time, this ash will become part of the soil, contributing to fertility, supporting new growth. For now, though, it's simply a gray blanket, sterile and fresh, a new surface waiting for life to return. The lava cools more slowly. The thin flows cool in days or weeks, their surfaces hardening into rough, clinkery rock if the flow was gas-rich and turbulent, or into smooth, ropey rock if the flow was quieter and more fluid. The thick flows and domes cool over months or years, cracking as they contract, creating columnar joints and polygonal patterns that reveal the internal stress and cooling history of the rock. Steam rises from cracks and vents in the cooling lava, especially when rain falls on the still hot surface. The hiss of water flashing to steam is one of the characteristic sounds of a cooling lava flow, a reminder that even solid-looking rock can hold enormous amounts of heat. Beneath the surface, the magma chamber has changed. It has lost volume, lost pressure, lost heat through the eruption. The remaining magma settles, cools, begins crystallizing again. The walls of the chamber may collapse slightly inward, adjusting to the new, lower volume of melt. This adjustment can cause additional small earthquakes, a trailing off sequence of tremors, as the system finds a new equilibrium. The volcano is returning to rest, its systems winding down, the urgency of release giving way to the long, slow process of recovery. This is the pattern. Release, then calm. The eruption, no matter how intense it seemed in the moment, is brief compared to the quiet that follows. Days or weeks of activity, then years or decades or centuries of quiet. The volcano's default state is not eruption. Its default state is rest. And in this rest, it rebuilds slowly, patiently, gathering the materials and pressure for the next cycle if and when that cycle comes. Over longer timescales, over thousands and tens of thousands of years, repeated eruptions build the volcanic edifice. Each flow of lava adds a layer. Each fall of ash adds a layer. These layers accumulate, one atop another, constructing the familiar cone shape of a stratovolcano, or the broad, gentle slopes of a shield volcano, depending on the type of eruptions and the composition of the magma. The cone is not built in a single event. It is built eruption by eruption, layer by layer, a slow construction that happens in pulses separated by long intervals. The shape of the volcano reflects the behavior of its magma. Basaltic magmas, which flow easily, build broad shields with gentle slopes, because the lava can travel far from the vent before solidifying. The Hawaiian Islands are shield volcanoes, built from countless thin basalt flows, piled atop one another over hundreds of thousands of years. The slopes are so gentle you can walk up them without much effort. A few degrees of incline, the whole structure more like a dome than a mountain. Andesitic and rhyolitic magmas, which are more viscous, build steeper cones because the lava and pyroclastic material don't travel as far. They pile up near the vent, creating the classic steep-sided peak that many people envision when they think of a volcano. Between eruptions, the volcano's surface is subject to the same erosional processes that shape all landscapes. Rain falls and runs off, carving gullies and channels into the loose ash and the fractured lava. Freeze-thaw cycles crack the rock, water seeping into fractures, freezing and expanding, wedging the rock apart. Gravity pulls loosened material downslope, creating talus slopes and debris fans. The sharp, fresh edges of new volcanic rock begin to soften, to round, to weather. Plants return in stages. The first colonizers are often mosses and lichens, organisms that can grow on bare rock, extracting nutrients from the minerals in the stone and from the air. They're extraordinarily patient, growing slowly, sending roots into tiny cracks, breaking down the rock a little more with each generation. After them come grasses and small herbaceous plants, species that can tolerate poor soil and harsh conditions. Their roots stabilize the ash. Their dead leaves and stems add organic matter, beginning the slow transformation from sterile volcanic debris to living soil. Shrubs arrive next, then small trees, then eventually the full forest, if the climate allows it. This succession can take decades or centuries, depending on the starting conditions and the local environment. On some volcanoes, the return of vegetation is surprisingly quick. Within a few years, the black lava fields are dotted with green, and within a few decades, they are covered. On others, especially in arid climates, or where the eruption was particularly destructive, the recovery is slower, more tentative, but it happens nonetheless. Life is persistent, and the nutrients in volcanic rock make excellent soil once weathering has done its work. The volcano itself, the geological structure, continues to evolve. Erosion carves canyons into the flanks, exposing the internal layering of lava and ash. Streams cut down through the layers, sometimes revealing old conduits and dikes, ancient pathways where magma once flowed, now solidified into resistant rock that stands out from the softer surrounding material. The summit may collapse inward if the magma chamber below empties and the overlying rock is no longer supported, forming a caldera, a wide, basin-like depression that can be kilometers across. This collapse is not a sudden, catastrophic event in most cases. It's a gradual subsidence, the ground settling downward over hours or days as support is withdrawn from below. The volcano's relationship with the magma system beneath it can change over time as well. The supply of magma from the mantle may weaken. The tectonic conditions that allowed magma to form in the first place may shift. Plate boundaries move, hotspots migrate relative to the overlying plate, and the volcano finds itself no longer positioned above a source of melt. When this happens, the eruptions become less frequent. The intervals between them stretch from centuries to millennia. The magma chamber cools, crystallizes, becomes more solid than liquid. The pathways that once carried magma become clogged with solidified rock. And without fresh magma to reopen them, they remain closed. This is the volcano aging, moving into a quieter phase of its existence. The system is still there, still potentially capable of activity, but the urgency has faded. The volcano takes longer naps in between smaller awakenings. The signals of activity the earthquakes, the ground deformation, the gas emissions, become less frequent, less pronounced. The volcano is transitioning from active to dormant, though the boundary between these categories is not sharp. A volcano is considered active if it has erupted recently, within the last several thousand years. It's considered dormant if it hasn't erupted recently, but still has the potential to do so. It's considered extinct if the magma source has been cut off entirely and no future eruptions are expected. But even extinct volcanoes are not entirely finished. The heat they brought to the shallow crust doesn't disappear overnight. It dissipates slowly over tens of thousands of years. Springs and fumaroles may continue to vent at the surface, gentle reminders of the warmth below. The water emerging from these springs has been heated by the residual heat of old magma, or by the hot rock that surrounded the magma chamber, or by the slow decay of radioactive elements in the crust. The heat is diffuse now, spread out, no longer concentrated enough to melt rock, but still enough to warm water, to create steam, to maintain small pockets of unusual thermal activity in the landscape. Geothermal systems like this can persist for a very long time. Yellowstone, for instance, is a volcanic system with a magma chamber still present at depth, and its geysers and hot springs are direct expressions of that ongoing heat. But even much older volcanic systems, ones where the magma has long since solidified, can have warm springs and gas vents if the heat is dissipating slowly enough, and if there are pathways for water to circulate down, heat up, and return to the surface. These features are quiet, benign, often beautiful. They create unique ecosystems where thermophilic organisms, heat-loving bacteria, and archaea thrive in waters that would be lethal to most life. The bright colors of some hot springs come from these microbial mats, communities of organisms that have adapted to temperatures that can approach boiling. The late life of a volcano is largely a story of surface processes. Weathering and erosion dominate. The volcanic rock, once fresh and strong, gradually breaks down under the assault of water, ice, temperature fluctuations, and chemical reactions. Basalt, for example, weathers relatively quickly in humid climates because the minerals it contains, pyroxene, olivine, plagioclase, are not stable at surface conditions. They react with water and carbon dioxide in the air, transforming into clays and iron oxides. This weathering releases the nutrients locked in the minerals, and the resulting soil is often very fertile, which is why volcanic regions, despite the periodic hazard of eruptions, are often densely populated and agriculturally productive. Andesite and rhyolite weather more slowly because their minerals, especially quartz, are more resistant to chemical breakdown. But even these rocks eventually succumb. Freeze-thaw cracking is particularly effective in cold climates. Water enters cracks, freezes, expands with tremendous force. Water expands about 9% when it freezes, and this expansion can generate pressures sufficient to fracture even the hardest rock. Each freeze-thaw cycle widens the crack a little more, and eventually the rock splits, breaks, falls. The talus slopes at the base of many volcanic peaks are built from this process. Thousands of years of freeze-thaw cycles, gradually dismantling the mountain. Glaciers, where they occur, are even more effective at erosion. A glacier is an immense sheet of ice that flows under its own weight, grinding over the landscape beneath it. The ice carries rocks and debris embedded in it, and this debris acts as an abrasive, scouring the bedrock, plucking blocks free, carving deep valleys. Many of the world's most dramatic volcanic landscapes have been shaped by glaciation. Mount Rainier, Mount Hood, the volcanoes of Iceland, the peaks of the Andes. The smooth, U-shaped valleys and the polished bedrock are the glacier's signature, evidence of ice that may have melted thousands of years ago, but which fundamentally reshaped the volcanic edifice during its presence. Wind also plays a role, especially in arid regions. Wind can transport fine particles, ash and dust, carrying them away from the volcano and depositing them elsewhere. Over time, this can remove entire layers of ashfall, redistributing the material across the landscape. The wind-sculpted surfaces of some volcanic rocks, the smooth curves and hollows, are the result of millions of tiny particle impacts, sandblasting on a geological scale. All of these processes work together to lower the volcano, to soften its contours, to blend it back into the surrounding landscape. The sharp summit becomes rounded. The steep slopes become gentle. The dramatic peak becomes a modest hill, and eventually, over millions of years, even the hill erodes away, leaving only the roots of the volcano, the solidified magma chamber, and the dikes and sills that radiated from it, harder and more resistant than the surrounding rock, standing as low ridges or isolated knobs in an otherwise eroded plain. This is not failure. This is the completion of the cycle. The volcano has done its work. It has brought material from the Earth's interior to the surface, added to the crust, built new land, and now it allows the surface processes to reclaim it, to break it down, to distribute its minerals into the soil and the sea. The atoms that made up the magma will become part of sediments, part of new rocks, part of living organisms. The cycle continues, but the volcano itself has finished its active role. In thinking about volcanoes this way, as long-lived systems that spend most of their time quiet, we find a useful metaphor for our own experiences of pressure and release. Stress accumulates in the body and mind, much like pressure accumulates in a magma chamber, gradually, incrementally, often without our full awareness. We feel the subtle signs: tension in the shoulders, a clenched jaw, a mind that won't stop circling the same thoughts. These are the body's equivalent of ground inflation and micro-earthquakes, small signals that something is building. And just as a volcano doesn't need to explode to release pressure, it can vent gas, extrude lava slowly, deflate gradually. We don't need dramatic outbursts to let go of the tension we carry. A slow, deep breath is a pressure release. A quiet walk is a release. Sleep itself is perhaps the most fundamental release, the nightly letting go of the day's accumulated stress, the slow cooling and settling of an active mind. The volcano teaches patience with this process. Pressure doesn't have to be released immediately or forcefully to be released effectively. The earth holds its heat and pressure for as long as it needs to. And when the release comes, it comes naturally, in its own time, in whatever form is appropriate to the conditions. There is no urgency, no panic, no sense that something terrible will happen if the release doesn't occur right now. The volcano simply waits, and when the moment is right, it lets go. This same patience is available to us. The breath that releases tension doesn't have to be forced or rushed. It can be as slow and deliberate as lava cooling. Each exhale a gentle letting down. Each inhale a calm gathering before the next release. The mind, too, can cool like volcanic rock. Thoughts that were molten and fluid gradually solidifying into something quieter, more stable, less urgent. The body can settle like ash, each muscle relaxing, each point of tension easing, until you are resting on the surface of yourself, soft and still. The pattern is the same. Long quiet, small release, long quiet again. This is the rhythm of the volcano, and it can be the rhythm of falling asleep. Long moments of stillness, broken occasionally by a shift in position, a deeper breath, a fleeting thought that rises and then fades. Then stillness again, deeper this time, more complete. The cycles continue, each one quieter than the last, until you are fully at rest, as deeply at rest as a volcano that has slept for 1,000 years. Imagine now the darkness underground, the depth where pressure is high and time is slow. There is no need to be there, no need to descend. You are simply aware that it exists, that deep foundation of the earth, that reservoir of heat and patience. It has been there for billions of years. It will be there for billions more. It requires nothing from you. It simply is, vast and quiet and warm, in a way that is comforting rather than threatening. Above that depth, the cooler layers, the crust where rock is solid and stable. The ground beneath you as you lie in bed is part of this crust, ancient and patient, supporting you without effort, without complaint. It has supported mountains and forests and oceans. It supports you now with the same effortless stability. You can release your weight into it fully, trusting that it will hold you, that there is no need to hold yourself up to maintain tension, to stay alert. The ground has you. The bed has you. You can let go. And on the surface, the slow processes of weather and time. Rain falling in the darkness. Each drop a tiny impact. Countless impacts smoothing the world, wearing away the sharp edges. The rain is patient. It doesn't rush. It falls steadily, quietly. A gentle persistence that reshapes everything given enough time. Your breath can be like that rain, steady and quiet. Each breath a small release. Countless small releases that together create deep rest. The ash settling, which we spoke of earlier, is another image for the quieting mind. Thoughts that were airborne, suspended, drifting, gradually settling, coming to rest on the landscape of your awareness. Some thoughts fall quickly and land close. Others drift farther before settling. But all of them eventually find a place to rest and the air clears. And what remains is stillness. A soft, grey quiet, where nothing is urgent and everything can wait until morning. The lava cooling is the body relaxing, the heat of the day's activity gradually dissipating, the surface cooling first, forming a protective crust of calm, while the interior remains warm and safe. The warmth doesn't have to leave entirely. You can be cool on the outside, relaxed and still, while remaining warm within, the core temperature of your body maintained effortlessly by the autonomic systems that require no conscious thought, no effort, no vigilance. The volcano's long sleep is your sleep. The volcano rests for centuries. And in those centuries, Meitsen is not waiting anxiously. It is not impatient. It is simply resting, because that is what it does between the brief moments of activity. And you can rest the same way, not waiting for something, not preparing for something, just resting because this is the time for rest, because the night is here, because your body and mind have earned this quiet, this long, deep settling into stillness. There is no need to monitor the small signals anymore. No need to attend to the micro-earthquakes of thought or the slight inflations of concern. The monitoring can stop. The attending can stop. You can trust that the systems will take care of themselves, that the pressure will equalize naturally, that the release will happen when it needs to happen, and that right now, in this moment, the only thing required is rest. The darkness around you is not empty. It is full of quiet, full of the slow processes that happen when the world is left alone to do what it does. Rain falling somewhere, wind moving through trees, the earth cooling and settling and holding its vast reserves of patience. You are part of this. You are resting in the same darkness, held by the same patient systems, cooling and settling and releasing in the same slow, natural way. And as you rest, you can notice that there is less to notice. The thoughts are fewer. The sensations are softer. The urgency has drained away like heat dissipating into the night. What remains is just the basic fact of being here, lying down, breathing slowly, held safely, with nothing to do and nowhere to go, and no pressure to be anything other than exactly this. A warm, quiet presence, resting in the dark, as still as stone, as patient as the earth, as deep as sleep. The volcano sleeps in its mountain, and you sleep in your bed, and the long quiet surrounds you both, undemanding and complete. Time passes, but there is no need to measure it. The night is long enough. The rest is deep enough. Everything that needs to happen will happen on its own, in its own time, with the same natural inevitability that governs the cooling of lava and the settling of ash and the slow, slow turning of the earth beneath the stars. You are allowed to rest this way, deeply, quietly, for as long as you need. There is no pressure to release because the release is already happening with each breath, with each moment of stillness, with each small letting go. The volcano has shown you the way. Long quiet, brief release, long quiet again. And in this moment, you're in the long quiet, the deep rest, the patient dark, where nothing is required and everything is held, and you can simply be, breathing softly, cooling gently, settling into sleep the way ash settles onto the earth, soft and complete and perfectly, perfectly still. The next story is about to begin. Please relax and enjoy. A mountain is not a thing that suddenly appears. It is not an object that arrives one morning and remains unchanged until it disappears. A mountain is a process made visible, a slow conversation between forces that push upward and forces that wear downward, all happening at the same time, over stretches of time so long that human lifetimes vanish into them like single raindrops into an ocean. To understand a mountain is to understand patience itself, to see how Earth does enormous work without hurry, using quiet forces and endless repetition. The mountain becomes a guide for sleep because it teaches us that nothing needs to be solved quickly, nothing needs to be forced, and everything important happens slowly, gradually, inevitably. Before there is a mountain, there is still something. The land might be lower and quieter, perhaps a broad plain stretching toward distant horizons, perhaps a shallow sea floor where water moves gently over sand and mud, perhaps a wide basin where rivers slow down and drop their sediment in thin layers that accumulate year after year, century after century, millennium after millennium. Time is already moving in this before chapter, but nothing looks dramatic from a human perspective. If you could stand in this landscape, you would see flatness, or gentle undulations, or water covering everything in a calm sheet. You would not see a mountain, because the mountain does not exist yet. But the future mountain is already being prepared deep below in the slow architecture of Earth's interior. In this quiet time before uplift, sediment settles, Rivers carry tiny particles of rock and mineral from distant highlands, places that are themselves old mountains, slowly wearing away. And when those rivers reach flatter ground or open water, they slow down. When water slows, it loses its ability to carry heavy particles. So sand drops first, then silt, then the finest clay. These materials settle onto the bottom in layers. Each layer is thin, sometimes just a fraction of an inch, sometimes a few inches, but they keep coming. Spring floods bring new sediment. Summer rains wash more particles downstream. Autumn and winter add their contributions. Over thousands of years, the layers pile up. Over millions of years, they become thick sequences of rock in the making. As new sediment arrives and settles on top of older layers, the older layers are buried deeper. The weight of everything above presses down. Water is squeezed out from between the grains. Minerals dissolved in that water begin to precipitate and act like natural cement, binding the grains together. What was once loose mud becomes mudstone. What was once sand becomes sandstone. What was once the skeletal fragments of tiny sea creatures becomes limestone. The rock is being compacted, hardened, transformed by pressure and time. This is how sedimentary rock forms, and it happens quietly, without fanfare, without anyone watching. The future mountain is simply waiting inside this slow preparation, layer upon layer, resting under the surface. Beneath these accumulating layers, deeper forces are at work. Earth's interior is not static. The planet's outer shell, the lithosphere, is broken into large pieces called tectonic plates, and these plates float on a softer, slowly flowing layer of rock beneath them. The rock in this deeper layer, called the asthenosphere, is hot enough to flow very slowly over geological time, driven by heat escaping from Earth's core and by the slow churning of convection currents. These currents push and pull on the plates above, moving them across the surface at rates of a few centimeters per year, about as fast as your fingernails grow. It sounds slow, and it is, but over millions of years, this movement adds up to thousands of kilometers. When tectonic plates move, they sometimes move apart, creating gaps where new crust forms. Sometimes they slide past each other, grinding along their edges. And sometimes they move toward each other, colliding. When two plates converge, something has to give. If one plate is made of denser oceanic crust, and the other is made of lighter continental crust, the denser plate usually sinks beneath the lighter one in a process called subduction. But when two pieces of continental crust collide, neither wants to sink. Continental crust is too light, too buoyant. Instead of one plate sliding smoothly under the other, they crumple together. They push against each other. Rock that was lying flat gets folded, compressed, thickened, and lifted upward. This is the beginning of mountain building, and it is called orogeny, from the Greek words for mountain and birth. The collision between tectonic plates does not happen quickly. The plates move toward each other over millions of years, and the effects accumulate gradually. At first, the changes might be subtle. A basin that was slowly filling with sediment begins to experience gentle compression, layers of rock that were horizontal start to tilt slightly. Faults, fractures in the crust, begin to form as the rock adjusts to new stresses. Some blocks of rock are pushed upward relative to others. The landscape begins to rise, but so slowly that if you could stand there and watch for a human lifetime, you might not notice any change at all. It is like watching the hour hand of a clock. You know it is moving, but you cannot see it move. Over long stretches of time, the compression continues. Rock layers that were once flat are folded into gentle curves, then into tighter folds, then into complex structures where layers loop back on themselves. Deep underground, the pressure and heat can become so intense that rocks change their mineral structure without melting, transforming into metamorphic rocks. Harder, denser, more crystalline. Granite forms from the slow cooling of magma deep below the surface. Schist and gneiss form from the alteration of older rocks under pressure. The crust thickens, and as it thickens, it also rises, pushed upward by the buoyancy of the thickened crust floating on the denser mantle below. Valleys become higher ground. Gentle slopes become steeper. The mountain begins not as a sharp peak, but as a broad swelling. An upward tendency, a rising of the land. This uplift is often too slow to see in any human time frame, but it is relentless. In some regions, the land rises a few millimeters per year. In particularly active zones, it might rise a centimeter or more per year. A centimeter per year means 10 meters per 1,000 years, 100 meters per 10,000 years, 1,000 meters per 100,000 years. Over 1,000,000 years, that centimeter per year becomes 10 kilometers of vertical motion, though not all of that motion translates into mountain height because other processes are already at work, lowering the surface even as the deep crust pushes upward. The mountain is being built and unbuilt at the same time, from the very beginning. As rock rises and the land becomes higher, the surface is exposed to air, water, and temperature changes. The moment the mountain becomes higher than the surrounding land, it begins to meet weather more directly. Atmospheric circulation patterns change around elevated terrain. Moist air, moving across the landscape, encounters the rising ground and is forced upward. As air rises, it expands and cools. Cool air cannot hold as much moisture as warm air, so water vapor condenses into droplets, forming clouds. If the air continues to rise and cool, the droplets grow larger and eventually fall as precipitation, rain at lower elevations, snow at higher elevations. The mountain, simply by being tall, creates its own weather patterns. It pulls moisture from passing air masses and receives more precipitation than the lowlands around it. Rain arrives and lingers on the mountain slopes. It collects in tiny depressions and flows downhill, following the path of least resistance. Gravity is constant and patient, always pulling water toward lower ground. The water finds cracks in the rock. Natural fractures form during the folding and faulting of the crust, and begins to widen them. Water seeps into these cracks, and when temperatures drop at night or during winter, the water freezes. Ice takes up more space than liquid water, so freezing water exerts tremendous pressure on the surrounding rock, wedging the crack open just a little bit more. When the ice melts, the crack is slightly wider than before, and more water can enter. The cycle repeats. Freeze and thaw, season after season, year after year. Each cycle widens the crack by a fraction of a millimeter. But over centuries and millennia, these tiny increments add up. Eventually, pieces of rock break free and tumble downslope. This process is called mechanical weathering, and it is one of the primary ways that solid rock is broken into smaller fragments. Temperature changes alone can cause weathering even without freezing. During the day, especially in sunny, high-altitude environments, rock surfaces can become quite warm. At night, they cool rapidly. Rock expands slightly when heated and contracts when cooled. Different minerals within the rock expand and contract at different rates, creating internal stresses. Over many cycles of heating and cooling, these stresses can cause the rock to crack and flake. The outer layers of rock sometimes peel away in sheets, a process called exfoliation, leaving smooth, rounded surfaces behind. While mechanical weathering breaks rock into smaller pieces, chemical weathering changes the rock's composition. Rainwater is slightly acidic because it absorbs carbon dioxide from the atmosphere, forming a weak solution of carbonic acid. When this acidic water comes into contact with certain minerals, especially those found in limestone and marble, it dissolves them slowly. The calcium carbonate in these rocks reacts with the acid, forming soluble compounds that are carried away in solution. Even minerals that seem very stable, like the feldspars found in granite, can be altered by chemical reactions with water and acids. Feldspar slowly breaks down into clay minerals, which are much softer and easier to erode. Chemical weathering is slower than mechanical weathering in cold climates, but in warm, wet environments, it can be the dominant force. The mountain is born into a world that immediately begins shaping it. From the moment rock rises above the surrounding terrain and becomes exposed to the atmosphere, it starts to change. It does not resist this change. It cannot. The forces of weathering are gentle but unceasing. There is no pause, no rest, no period when the mountain is exempt from the influence of water, air, and temperature. The mountain's life includes both building and unbuilding from the very start, and this dual nature defines its entire existence. As uplift continues and the land rises higher, the mountain's surface becomes rougher and more angular. The edges are sharp where rock has recently fractured. Slopes are steep and raw, not yet smoothed by long erosion. This is the mountain in its youth, tall, jagged, dramatic. But even in youth, the processes of erosion are already at work, softening the edges, rounding the peaks, lowering the heights. Water is the primary agent of this erosion, and water is everywhere on the mountain. It falls as rain and snow, melts from ice, seeps from springs, and flows in countless small streams that trace intricate patterns across the slopes. The first streams and rivulets on a young mountain are tentative and searching. Water flows downhill, always choosing the easiest route, and those choices become patterns. A tiny groove in the rock surface channels a few drops of water. Those drops carry microscopic grains of sediment, and the friction of moving water and sediment gradually deepens the groove. More water is drawn to the groove because it is the lowest point nearby, and the increased flow deepens it further. A tiny groove becomes a shallow channel. A shallow channel becomes a more defined drainage. Over time, the channel develops a characteristic cross-section, narrow at the top, where the stream is small, wider and deeper downstream, where tributaries join and the flow increases. Water always flows downhill, but the path it takes is influenced by the structure of the rock beneath it. If the rock has layers of varying hardness, common in areas of sedimentary or metamorphic rock, water will erode softer layers more quickly, creating steps and benches in the stream profile. If the rock is crossed by fractures or faults, water exploits these weaknesses, carving deeper channels along them. The mountain's internal structure, created during its formation, guides the pattern of erosion. Streams do not cut randomly across the landscape. They follow lines of weakness, zones of softer rock, areas where fractures are more closely spaced. Erosion is often described as destruction, but it is more accurate to think of it as transformation, or even as a kind of sharing. The mountain is not being destroyed, it is giving itself to the landscape. Grains of rock are loosened from the mountain surface and carried downhill by water. These grains, ranging from large boulders to fine silt, are sediment. and sediment is the raw material for new landscapes downstream. The mountain allows rivers to carry its material onward, distributing it across floodplains, depositing it in deltas, delivering it to the ocean where it will settle and, over geological time, become new sedimentary rock. The mountain is part of a cycle, and erosion is the mechanism by which it participates in that cycle. As streams cut deeper into the mountain, they create valleys. The cross-section of a valley depends on many factors: the hardness of the rock, the volume and velocity of the water, the steepness of the slope, the climate. In the early stages, valleys are often V-shaped, narrow at the bottom where the stream actively cuts downward, widening toward the top where weathering loosens rock from the valley walls and gravity pulls it downslope. The stream at the bottom of a V-shaped valley is actively eroding its bed, cutting deeper into the rock with the abrasive action of sediment carried in the flow. Boulders and pebbles roll and bounce along the stream bed, grinding against the underlying rock like natural sandpaper. Over long periods, the stream continues to deepen its valley, but the rate of downcutting slows as the valley becomes deeper. This is because the stream's gradient, the steepness of its descent, decreases as the valley floor approaches the level of the river or sea into which it ultimately flows. A gentler gradient means slower water velocity, which means less energy available for erosion. As downcutting slows, the stream begins to shift its energy toward widening the valley, meandering back and forth across the valley floor, undercutting the valley walls on the outside of bends and depositing sediment on the inside of bends. The valley shape gradually changes from a narrow V to a broader U, though this change is usually subtle and takes a very long time unless other factors intervene. While streams are carving valleys, the mountain as a whole continues its slow transformation. Uplift may still be ongoing, adding new height even as erosion lowers the surface. In many mountain ranges, this competition between uplift and erosion continues for millions of years. The mountain maintains its height, or even grows taller, not because erosion has stopped, but because new rock is being pushed upward from below at a rate equal to or greater than the rate at which the surface is being lowered. This creates a kind of dynamic equilibrium, a balance between opposing forces. It is calming to think about. Two processes working in opposite directions, neither winning completely, finding a steady middle ground, like breath finding an easy rhythm. Eventually, though, the forces driving uplift begin to weaken. The tectonic collision that created the mountain slows or stops as the plates involved change their motion or as the compressional stress is relieved. The supply of new upward motion decreases. Erosion, however, does not stop. It continues at its patient pace, and now it begins to win the long competition. This marks the transition from the mountain's youth to its middle age, the portion of its existence that fills most of its lifespan and is, in many ways, the quietest and most meditative part of its story. The mountain's long middle age is characterized by rhythm and repetition. Seasons repeat. Snow arrives in winter, covering the high peaks and slopes in a blanket of white. The snow accumulates, layer upon layer, compressing under its own weight. In spring, temperatures rise and the snow begins to melt. Meltwater trickles down the slopes, feeding streams and rivers, soaking into the soil, filling ponds and lakes. Summer brings different weather, perhaps thunderstorms in some regions, dry heat in others, and the mountain's appearance changes with the season. Vegetation grows. Flowers bloom at high elevations. Insects and animals move through the landscape. Autumn arrives with cooler temperatures and changing light. Plants prepare for winter. Snow returns. The cycle completes and begins again. Rain darkens the stone when it falls, turning gray, rock charcoal, brown rock sepia, red rock rust-colored. As the rain stops and the sun emerges, the rock dries, returning to its lighter shade. This simple cycle of wetting and drying happens countless times, and each time it contributes minutely to the weathering process. Water carries dissolved minerals to the surface, where they precipitate as the water evaporates, sometimes forming colorful crusts or stains. Water also carries acids from decaying vegetation, which enhance chemical weathering. The mountain surface is constantly being altered, constantly responding to the presence or absence of moisture. Freeze-thaw cycles continue to widen cracks. In autumn, water seeps into fractures during rainy periods. As winter approaches and temperatures drop, that water freezes. The ice expands, forcing the crack open. In spring, the ice melts, and the crack is left slightly wider than before. Pieces of rock loosen over time. Some fall immediately, tumbling down steep slopes and adding to the talus, the pile of broken rock fragments that accumulates at the base of cliffs and steep faces. Others remain perched precariously, held in place by friction or by the irregular shape of the fracture, until some future event, a particularly strong freeze, a heavy rain, an earthquake, dislodges them. The mountain does not resist this process. It cannot. Resistance would require some active force pushing back against the weathering, and mountains are not animate. They do not have will or intention. They simply exist, subject to the same physical and chemical laws that govern everything else on Earth. The mountain changes because it must, because the conditions surrounding it demand change, because water and air and temperature act on rock and rock responds. There is a kind of peace in this inevitability, a reminder that acceptance is built into the nature of things. Rivers carve valleys with quiet persistence. The water flows continuously, except in the driest climates or the coldest winters, and the flowing water carries sediment. The sediment acts as an abrasive, grinding against the bedrock of the stream channel. This abrasion is not violent or sudden. It is the accumulation of countless tiny impacts, sand grains bouncing along the bottom, pebbles rolling downstream, boulders shifting during floods. Each impact removes a microscopic amount of rock. Over decades, the cumulative effect is measurable. Over millennia, it is dramatic. Valleys deepen not through force, but through repetition. As valleys deepen and widen, the mountain shape becomes more recognizable. Ridges form between adjacent valleys, high points of rock that have not yet been eroded away. Saddles appear where two valleys approach each other from opposite sides of a ridge, creating low points along the ridgeline. Bowls and cirques develop at the heads of valleys, especially in areas where winter snow accumulates and persists. These features give the mountain its characteristic topography, its unique silhouette against the sky. But none of these features appear suddenly. Each is the result of countless small events, countless days of weathering and erosion, countless repetitions of freeze-thaw cycles, rainstorms, snowmelt, and stream flow. In the mountain's middle age, life begins to play a more visible role. As climate allows, plants take root in the thin soils that develop from weathered rock. Soil formation is itself a slow process. Rock must be broken into small particles, and those particles must be mixed with organic matter, decayed leaves, dead roots, animal waste, Microorganisms break down the organic matter, releasing nutrients that plants can use. The first plants to colonize rocky slopes are often lichens and mosses, which can survive in harsh conditions with minimal soil. Lichens are particularly important because they contribute to chemical weathering, secreting acids that help break down the rock surface. As lichens and mosses grow, die, and decay, they add organic matter to the developing soil, making it possible for more complex plants to establish. Grasses are often the next arrivals. They have extensive root systems that help stabilize slopes, reducing erosion. The roots penetrate cracks in the rock, widening them as the roots grow, contributing to mechanical weathering. When grasses die, their roots decay and add organic matter to the soil. Over time, the soil deepens and can support shrubs and eventually trees. The type of vegetation that can grow at any particular location on the mountain depends on many factors: altitude, slope aspect, water availability, soil depth, temperature. Lower slopes, which are warmer and often have deeper soil, can support forests. Higher slopes, where temperatures are cooler and soil is thinner, support grasses and shrubs. The highest elevations, where conditions are most severe, may support only lichens, mosses, and a few hardy flowering plants. Ecosystems develop on the mountain as another layer of its biography. Life adapts to the gradients of altitude, temperature, moisture, and sunlight. Different species occupy different niches. Some plants thrive on south-facing slopes, where sunlight is more intense. Others prefer north-facing slopes, where conditions are cooler and moister. Some animals live in the forests of the lower slopes, while others are adapted to the alpine meadows and rocky terrain of the high country. Birds nest on cliff faces. Insects pollinate flowers. Small mammals burrow in the soil. Predators hunt prey. The mountain becomes a set of interconnected habitats, each with its own community of organisms. Life on the mountain is not static. Climate shifts over geological time, and as climate changes, so do the ecosystems. During warmer periods, tree line, the elevation above which trees cannot grow, shifts upward. Forests expand into areas that were previously too cold or too harsh. During cooler periods, tree line shifts downward. Forests retreat, and alpine vegetation expands. These shifts happen gradually, over centuries and millennia, as species migrate or disappear, as soils develop or erode, as temperature and precipitation patterns change. Through all of this, the mountain remains steady in its slow transformation, providing the physical substrate on which life plays out its endless variations. In some climates and at some elevations, snow can persist from year to year, never fully melting even in summer. When this happens, snow accumulates and compresses under its own weight. The individual snowflakes lose their delicate shapes and become rounded grains of ice. As more snow falls and compresses, the grains are packed more tightly together. Air is squeezed out. The material transitions from snow to firn, a transitional stage between snow and ice, and eventually to glacial ice, which is dense, hard, and blue-tinted. This process takes years or decades, depending on the rate of snowfall and the temperature. A glacier forms when ice accumulates to sufficient thickness that it begins to flow under its own weight. Ice is a solid, but on geological timescales and under pressure, it behaves like a very viscous fluid. It deforms slowly, creeping downslope in response to gravity. The movement is almost imperceptible, perhaps a few meters per year for a typical mountain glacier, though some glaciers move faster and some move more slowly. The ice does not melt and refreeze as it moves. Rather, the entire mass of ice deforms internally, with ice crystals sliding past each other along internal planes of weakness. Glaciers reshape valleys in distinctive ways. Unlike rivers, which erode primarily at the bottom of their channels, glaciers erode both the floor and the walls of the valleys they occupy. The ice plucks rocks from the bedrock by freezing onto them and then pulling them away as the glacier moves. This plucking is most effective on the downstream side of bedrock bumps and on valley walls, where the ice exerts pressure. The rocks that are plucked from the bedrock become embedded in the ice and act as additional abrasive tools. As the glacier flows, these embedded rocks grind against the bedrock below and beside the ice, smoothing and polishing the surface, carving long scratches called striations that indicate the direction of ice flow. Over time, a valley occupied by a glacier changes shape. The V-shaped cross-section, typical of a river valley, becomes a U-shaped cross-section. The valley floor is widened and flattened. The valley walls are steepened and smoothed. At the head of the glacier, where snow and ice accumulate, the ice carves a circular or semicircular depression called a cirque. Cirques have steep back walls and gentler, outward-sloping floors, and they are often the sites of small lakes after the glacier melts. Multiple cirques around a single peak can create a sharp, pyramidal mountain summit sculpted by ice approaching from several directions. Glaciers are most effective at erosion in cold climates, particularly during ice ages, when glaciers expand and cover much larger areas. During the last ice age, which ended about 11,000 years ago, ice sheets covered large portions of North America, Europe, and Asia. Mountain glaciers expanded far down their valleys, reaching elevations and latitudes where they no longer exist today. These expanded glaciers carved and reshaped mountain landscapes on a massive scale, creating the dramatic scenery visible in many high mountain ranges today. But even during ice ages, glaciers moved slowly. The reshaping of valleys was the result of thousands of years of glacial flow, not sudden catastrophic events. When glaciers retreat, either because climate warms or because the supply of snow decreases, they leave behind clear evidence of their presence. Polished bedrock surfaces, scratched with striations, mark areas where ice once flowed. Erratic boulders, rocks carried by the ice and deposited far from their source, rest on surfaces of entirely different rock types. Moraines, piles of sediment deposited by the glacier, mark the glacier's former extent. These moraines can be lateral, forming along the sides of the valley, terminal, marking the farthest advance of the ice, or ground moraines, spread across the valley floor as the ice melted. The landscape left behind by a retreating glacier is often rugged and irregular, with lakes filling depressions carved or dammed by the ice, and streams flowing over bedrock or through piles of glacial sediment. The retreat of glaciers is another way the mountain shares itself with the world. The sediment carried by glacial ice, ground up rock, ranging from fine clay to large boulders, is deposited as the ice melts, creating new landforms and new soils. Rivers fed by glacial meltwater carry some of this sediment downstream, distributing it across floodplains and deltas. The minerals in glacial sediment can be rich in nutrients, making glacially fed rivers particularly productive for the ecosystems they support. The mountain, through the action of its glaciers, contributes to the fertility of distant lowlands. Throughout the mountain's middle age, uplift might not have stopped entirely. In many places, Earth continues to push upward, even while erosion lowers the surface. This ongoing uplift can be driven by several mechanisms. If the mountain range is still in a zone of tectonic compression, if the plates are still converging, even slowly, new uplift can continue. Alternatively, as erosion removes material from the mountain surface, the crust becomes lighter, and buoyancy causes it to rise slightly, a process called isostatic rebound. This rebound does not restore the full height lost to erosion, but it does allow the mountain to maintain elevation longer than it would if uplift had stopped completely. The result is a gentle tension, a kind of dynamic balance. The mountain is being lowered by erosion and raised by uplift at the same time. If the rates are equal, the mountain maintains a constant height, though individual particles of rock are constantly being cycled through, new material rising from below, while old material is carried away at the surface. If erosion exceeds uplift, the mountain gradually becomes lower. If uplift exceeds erosion, the mountain continues to grow, at least for a time. This balance is not static or permanent. It shifts over geological time as tectonic forces change and as climate variations alter the rate of erosion. But for long stretches of the mountain's middle age, this balance can hold, creating a period of relative stability. Water continues to organize the mountain's daily life. Storms feed streams. Streams become rivers. Rivers carry sediment to plains and deltas, and ultimately to the ocean. The mountain's rock turns into sand and silt and clay, materials that build soils, floodplains, beaches, and eventually new layers of sediment somewhere else. The mountain is constantly becoming other places. This is not loss. It is transformation. The mountain's atoms and minerals are redistributed across the landscape, becoming part of new systems, supporting new life, participating in new cycles. There is a quiet generosity in this process, a reminder that nothing in nature is isolated or self-contained. Everything is connected, everything flows, everything participates in larger patterns. The rivers that drain the mountain carry not just sediment, but also dissolved minerals. Chemical weathering releases ions into the water: calcium, magnesium, sodium, potassium, silica, and these dissolved substances travel downstream. Some precipitate out to form new minerals in the riverbed or floodplain. Some are taken up by plants and incorporated into living tissue. Some reach the ocean, where they contribute to the saltiness of seawater or are used by marine organisms to build shells and skeletons. When those organisms die, their shells sink to the ocean floor and accumulate as sediment, eventually forming limestone. The mountain, through its slow dissolution, helps create rocks on the seafloor thousands of kilometers away. This cycling of material is one of Earth's fundamental processes. Rock is uplifted, exposed to weathering, broken down, transported by water, deposited as sediment, buried, compacted, sometimes heated and altered, and eventually uplifted again in a new mountain-building event. The cycle is called the rock cycle, and it operates on timescales of tens to hundreds of millions of years. No single particle of rock experiences the entire cycle in a continuous sequence. Some get recycled quickly, some remain buried for hundreds of millions of years. But the overall pattern is clear. Mountains are temporary features on a dynamic planet. They rise, they erode, and they rise again elsewhere, in different forms, from the material of their predecessors. As the mountain's life continues, an uplift slows or stops entirely. Erosion gradually wins its long competition with the forces of elevation. Peaks become lower and rounder. Sharp edges soften. The mountain silhouette becomes gentler, less jagged, more worn, more relaxed. This is the mountain's later life phase, when the drama of youth has passed and the mountain settles into a quieter existence. Valleys widen as streams continue their patient work. Ridges narrow as erosion attacks them from both sides. High peaks are lowered as weathering removes material from their summits, and slopes. The landscape becomes smoother, with gentler gradients and less dramatic relief. This transition from rugged youth to rounded maturity is visible in many mountain ranges around the world. The young, high mountains, like the Himalayas, the Alps, or the Andes, have sharp peaks, steep slopes, and deep, narrow valleys. These are mountains where uplift is recent or ongoing, where the forces of elevation still compete vigorously with erosion. The old, worn mountains, like the Appalachians in eastern North America, the Urals in Russia, or the Scottish Highlands, have rounded summits, gentle slopes, and broad open valleys. These are mountains where uplift stopped long ago, where erosion has had tens or hundreds of millions of years to soften the landscape. The transition is not sudden. There is no moment when a mountain passes from youth to age. The change is gradual and continuous, driven by the unceasing work of water, temperature, ice, and time. The mountain's silhouette shifts imperceptibly from year to year, noticeably from century to century, dramatically from millennium to millennium. The mountain's effort, if we can call the tectonic forces that raised it effort, decreases as those forces wane and eventually cease. The mountain's form becomes smoother and more patient, as if it is learning to rest, learning to let go of the height it once achieved. There is no loss in this settling. The mountain does not mourn its decreasing elevation. It simply exists, subject to the same processes that have always acted upon it, responding to them in the only way it can. The rounded peaks of an old mountain are no less real, no less worthy than the sharp spires of a young one. They are simply at a different stage of the cycle, playing a different role in the landscape. The old mountains are often covered with thick forests and rich soils, their gentle slopes more hospitable to life than the harsh, steep faces of young peaks. They offer different beauty, different ecosystems, different experiences. Eventually, over immense stretches of time, what once stood high becomes a range of hills, then subdued highlands, then rolling terrain that still carries the memory of uplift in its rocks and structure. The rocks themselves tell the story. They are folded, faulted, metamorphosed, evidence of the compression and heat they experienced during mountain building. Geologists can read this evidence and reconstruct the mountain's history, even when the mountain itself is gone, worn down to near the level of the surrounding plain. The rock record is a kind of memory, preserving the mountain's past, even after its topographic expression has vanished. Sediment continues to travel away from the eroding highlands in rivers. The particles that once formed the mountain's highest peaks are carried downstream, deposited in floodplains, deltas, and the ocean. In floodplains, the sediment builds fertile soils. In deltas, it creates new land, extending the coastline seaward. In the ocean, it settles on the seafloor, joining other sediments in broad layers that will eventually compact and harden into sedimentary rock. The mountain's material reaches the ocean and rests again in layers, returning to a state similar to the before state where this story began. Layers of sediment accumulating, being buried, being compressed, waiting for the next cycle of uplift. This return is not an ending. It is a continuation. The sediment on the seafloor is not inert or finished. It is still part of Earth's active systems. It can be buried deeper by additional sediment. It can be altered by heat and pressure. It can be caught up in a new episode of tectonic convergence and uplifted again, becoming part of a new mountain range. The cycle is not circular in the sense that the same particles return to the same place. Rather, it is cyclic in the sense that the same processes repeat, using different material, in different locations, across deep time. In the closing perspective of the mountain story, we see the full cycle and allow it to feel soothing. Rock is uplifted by tectonic forces, creating mountains. Mountains are weathered by water, air, and temperature, breaking rock into sediment. Sediment is transported by rivers to lowlands and oceans. Sediment is deposited in layers, buried, and compacted into new sedimentary rock. Sedimentary rock is caught up in tectonic forces and uplifted again. The cycle continues, endlessly, patiently, without waste. Nothing is lost, everything is moved and reshaped. Even the mountain's end is a return, grain by grain, into new landscapes and future beginnings. There is deep comfort in this understanding. The mountain teaches us that change is not catastrophe. Erosion is not failure. The gradual wearing down of something tall and strong is not sad. It is participation in a larger pattern. The mountain shares itself with the world through its erosion, contributing to the fertility of valleys, the formation of soil, the creation of new land. Its atoms and minerals continue to matter, continue to be part of Earth's processes, long after the mountain's topographic peak has vanished. For those of us struggling with worry or stress, the mountain offers a metaphor without being preachy about it. Our worries can feel like sharp peaks in the mind, tall, imposing, immovable. But time and repetition soften even the hardest rock. We do not need to chisel our worries tonight. We can let them weather gently, one breath, one exhale, one quiet moment at a time. The mountain tells us that enormous work can be done slowly, that the most fundamental changes happen through patient repetition, that resistance is not always necessary or even possible. Sometimes acceptance is the natural response, the built-in response, the only response that makes sense. The mountain's existence is defined by two opposing forces finding balance: uplift and erosion, building and softening, rising and returning. These forces are not in conflict, even though they work in opposite directions. They are both necessary. Without uplift, there would be no mountain. Without erosion, the mountain's material would never return to the cycle, never feed new systems, never contribute to new creation. The balance between uplift and release, between accumulation and distribution, between height and patience, is what makes the mountain's life complete. As the mountain slowly wears away, as its peaks are rounded and its valleys widened, as its rock is carried grain by grain to the sea, there is no rush, no urgency, no panic. The mountain does not hurry. It cannot hurry. It exists in geological time, where 1,000,000 years is a reasonable interval, where change happens slowly enough to seem eternal from a human perspective, but fast enough to completely reshape continents given enough time. The mountain's pace is the pace of deep processes, processes that cannot be forced, processes that happen when and how they must, governed by physics and chemistry and the slow dance of tectonic plates. We can learn from this pace. Our own lives operate on different timescales, measured in heartbeats and seasons, rather than millennia. But the principle is the same. Important work does not require constant effort or dramatic action. Important work often happens quietly, through small repeated actions, through showing up day after day, through allowing processes to unfold at their natural speed. The mountain does not strain to rise or struggle to erode. It simply exists, and the forces acting on it do their work. We can simply exist too. allowing the forces in our lives, time, rest, healing, growth, to do their work without forcing them, without demanding immediate results. The mountain stands as a monument to patience. Every grain that falls from its peaks, every particle carried downstream, every atom redistributed into the world, is part of a process that has been happening for billions of years and will continue for billions more. The specific mountains change, new ones rise, old ones wear away, but the cycle continues. There is continuity in this. There is reliability. The processes that shape mountains are the same processes that have always shaped mountains, operating under the same physical laws, responding to the same forces. In a world that often feels chaotic and unpredictable, there is comfort in the steadiness of geological processes. As we imagine the mountain in its long, slow transformation, we can let that image quiet our thoughts. We can picture rainwater seeping into cracks, freezing on a cold night, melting in the morning sun. We can imagine the slow widening of those cracks, the eventual release of rock fragments, the tumbling descent down a slope. We can see those fragments resting at the base of a cliff, gradually being buried by more fragments, slowly weathering into smaller pieces, eventually being washed into a stream. We can follow the stream as it carries the fragments downstream, depositing them in a quiet eddy, picking them up again during a flood, carrying them farther, always farther, toward the ocean. There is no drama in this imagining, no tension, no conflict. There is only process, slow, natural, inevitable. The fragments do not resist their journey. They are carried where the water takes them, deposited where the water slows, picked up again when the water speeds up. They participate in the cycle without choice or agency, simply responding to the forces around them. We can let ourselves respond to forces in the same way, not with resistance or struggle, but with acceptance, with flow, with the understanding that some things will happen regardless of our effort, and that those things are not failures, but simply part of the pattern. The mountain, in its slow erosion, demonstrates that letting go is natural. The rock does not cling to the mountain. The mountain does not hold tight to its peaks. When a fragment is ready to fall, it falls. When a grain is ready to be carried away, it is carried away. There is no sadness in this, no sense of loss. There is only continuation, transformation, participation in something larger. The fragment that falls from the peak becomes part of the valley. The grain that is carried to the ocean becomes part of the seafloor. Nothing ends. Everything changes and continues. We can bring this understanding to our own experience of worry and stress. The thoughts that trouble us do not need to be chiseled away forcefully. They can be allowed to weather naturally, to soften over time, to gradually release their hold on us. We do not need to solve everything tonight. We do not need to force peace or demand sleep. We can simply exist, breathing quietly, allowing our thoughts to erode slowly, letting tensions settle like sediment sinking through still water. The mountain's timeline is vast, stretching across millions of years. But within that vastness, there are small moments. A single raindrop, a single freeze-thaw cycle, a single grain released. Our timeline is shorter, but it too contains small moments. A single breath, a single heartbeat, a single instant of stillness. The mountain is built from millions of small moments, and so are we. The mountain is worn away by millions of small moments, and so are our worries and tensions. Nothing dramatic needs to happen. Small moments, repeated patiently, are enough. As we settle deeper into this story, as we let the mountain's patient existence fill our awareness, we can feel our own pace slowing to match it. Our breathing slows. Our thoughts slow. The urgency that often drives our minds begins to fade, replaced by a quieter rhythm, a steadier pulse. We are learning from the mountain, absorbing its lesson of patience, embodying its acceptance of slow change. We are becoming as patient as stone, allowing our thoughts to erode, allowing our tension to settle, allowing sleep to arrive naturally, like water, finding its way downhill. The mountain does not hurry toward its end. It does not count the years or measure its decreasing height with anxiety. It simply is, moment after moment, day after day, millennium after millennium, existing in the only way it can, shaped by forces beyond its control, participating in cycles beyond its comprehension. It teaches us that we too can simply be, that we do not need to control everything, that we can trust the processes of rest and renewal to do their work without our constant supervision. In the deep quiet of the mountain's existence, there is room for us to rest. In the slow rhythm of uplift and erosion, freeze and thaw, rain and evaporation, there is a pattern we can follow into sleep. The mountain rises and falls, builds and releases, stands and erodes, and through it all, it remains itself. Rock being shaped by time, patient beyond measure, at peace with its transformation. We can be at peace with our own transformation, trusting that rest will come, that sleep will arrive. That morning will find us renewed, like the mountain after a storm, quietly continuing, patiently existing, softly weathering whatever comes. The next story is about to begin. Please relax and enjoy.